start with the webinar. So the webinar is about how the emissions norms are getting prevalent and how we are being a developing country and moving towards even more industrialization. Now, air pollution control norms are getting stricter in India. So with me today, I have three of our experts. Ravin Phadke sir, who is the technical director at RIECO Industries. He has an experience of more than 35 years. Dominic Chaco sir, he is an ESP expert, having worked with almost all of the ESP manufacturers and leading technical experts. And he also has an experience of more than 35 years. I also have with me Deepak Patil sir, who is the Central Proposal Head at RIECO Industries. And we would like to go ahead with the webinar. So the topic actually emerged from the changing norms that we are facing today. So I will show you a slide how the norms have changed in India in the next. So these are the basic norms that we could pull out from different state control boards or central pollution control boards. As you can see that the particulate matter norms have been increasing, have been getting stringent. So now we currently at RIECO, we are facing with customers who are actually demanding for PM particles less than 5 milligrams from today itself. Although the norm says it's to be about 10 to 20 milligram per Newton meter cube, but to be on the safe side and to be future ready, people are aiming for even stricter norms. Same goes for sulfur, nitrogen, carbon monoxide, hydrochloride, ammonia, and all the others. If you can see, within 3 years, the norms have drastically changed. And to actually make people aware and also make people aware about the solutions available in the industry that can be offered by RIECO, we are having this webinar. So I would like to ask Mr. Phadke sir to actually enlighten us about the new technologies that we have or the existing technologies that we have. How can we control the pollution and what kind of solution in different industry or setup we can use to eliminate different type of effluents. So over to Phadke sir.
Yeah, thank you, Arjun. Good afternoon, all of you. So air pollution control and air pollution in general is of course a hot topic today. One thing I would like to say is that air pollution is not just an environmental issue, but it affects our entire working. Now, for example, public health. World Health Organization has said that most of the, or a lot of, a big percentage of deaths that occur every year because of cardiovascular or respiratory diseases are attributable to air pollution control. Similarly, installing systems for air pollution control involves a lot of money. It involves spending of energy, and hence it touches every part of our working activity. But if we come to think of it, industrial growth, urbanization, and rising energy demand is something which is simply unstoppable. This is going to continue. So then the question arises as to how we minimize the environmental impact. So I think it's a combination of technology, regulation, and responsible operation. Now, when we talk about contaminants or pollutants, we know the conventional pollutants we hear always about, like, of course, the fine particulates, what we call as PM10 and PM2.5, or sulfur dioxide, we know about acid rain, or NOx, carbon monoxide, and nowadays also VOCs, which is volatile organic compounds. Similarly, you also have some hazardous pollutants. So we know of HF, HCl, H2S, benzene, dioxins, and some heavy metals like lead and mercury. There's also a third category which is being discussed globally, that is greenhouse gases. So here we have chemicals like carbon dioxide, methane, fluorinated gases, nitrous oxide, and so on. So all these kind of pollutants together have to be kept under control. Now, if we look at the sources from where these pollutants come to the atmosphere, a large part of industrial pollution comes from the manufacturing facilities and factories like thermal power plants, cement plants, iron and steel industries, chemical plants, fertilizer plants, refineries. Nowadays, semiconductor manufacturing, which is picking up in India, incinerators. And then there are also diffuse activities like, for example, construction activities, transportation, and biomass burning, which is also a problem in many areas. Now, when we talk about emissions, we have to consider two types, not just the stack emission we all know about, but also the fugitive emissions. Now, fugitive emissions basically arise in a factory, workshop, or shop floor. Basically during operations like the charging operation or handling of material in conveyors, storage of, say, solvents in tanks, and so on. Now, these fugitive emissions are also equally important because they directly affect the personnel, workers on the shop floor. So now the approach towards controlling this pollution is basically a three-pronged approach. The first one is to reduce the sources itself. So for example, when you are burning fuel, look at a better quality fuel which is going to pollute less. Use energy efficient systems. Use process optimization and minimize waste. So reducing at source itself is of course one of the important things to do. Second is capture and containment. So this is about the fugitive emissions I mentioned. So designing proper enclosures, suction hoods, and also having a effective ventilation system, especially when there is a heat stress, are important for the capture and containment. And this would directly give advantage to the working people in the plant. And the third one, of course, is our topic of interest, which is how to treat these emissions or how to treat these contaminants. So we know that we have essentially two types. One is the particulates, for which we have systems based on equipment like cyclone separators, which can give you a removal efficiency of 70% right up to 95-96%. Then we have back filters, pulse jet cleaning, which can give us an efficiency of more than 99%. Then we have electrostatic precipitators, which are also very effective in removing particulates and which are very convenient for handling large volumes of gas. And then we have scrubbing systems, which are especially good on trapping gaseous contaminants and vapors. And of course, we have scrubbers like Venturi scrubbers, which are also very effective on the particulate removal. Then when it comes to gaseous pollutants, like I mentioned, you have wet and dry scrubbers for sulfur dioxide, hydrochloric acid, hydrofluoric acid, ammonia vapors. For NOx, we generally talk about uh, selective non-catalytic and selective catalytic reduction. When it comes to VOCs, we have activated carbon adsorption, thermal oxidizers, and RTOs. Now, if we talk about the emerging technologies, because what I just mentioned are all existing for more than 50 years, though they are gradually developing and improving. The emerging technologies include carbon capture systems, plasma destruction units, and AI-enabled monitoring systems. So technology-wise, there has been a great deal of progress over the last 50 years on the pollution control front. But of course, a lot remains to be done. Now, when it comes to regulation, we know there are some key agencies in the country. The Ministry of Environment, Forest and Climate Change, the Pollution Control Board, central as well as state control board. So industries are required to get a consent to start and establish. Likewise, they require a consent to operate. Also, there are sector-specific standards. We have just shown the emission norms existing in the country. So there are also sector-specific standards which can be sometimes very stringent, like in case of hazardous waste incinerators. Another thing is industries have to install a continuous emission monitoring system, which is also now becoming an emerging trend, so that there is a continuous feedback available with the control boards to see how the pollution is being effectively controlled. So there is a growing emphasis on control of the very fine particulates, that is PM 2.5, then fluorides, VOCs, fugitive emissions, and also greenhouse gas accounting. So there is, I would say, a trend towards a convergence of climate change and air pollution, and they are not being dealt separately. So the future, it looks like, lies in integrated solutions. Now, if we look at the role of engineers, I would say they have to focus on process safety to prevent leaks. They have to consider occupational health to protect the workers, and of course, the environmental compliance to protect the communities. So the earlier philosophy of dilute and disperse is soon moving towards prevent, capture, treat, and continuous impact. So we look at pollution control as an investment in public health, sustainable industry, climate resilience, and of course, a better life for the future generations. Now, if we look at a good system, the judgment parameter is not just limited to so many milligrams per NFQ, but we have to also look at energy consumed per kilogram of pollutant removed. We have to look at the greenhouse footprint. We have to see the worker exposure, water consumption, the recoverable products generated, and so also ease of maintenance and digital integration. So if we now look at some of the systems which are typically operating in industry, I would like to take the steel industry, where we have high pressure gas coming out of a mini blast furnace. So a mini blast furnace, as we know, is used for producing pig iron. The furnace's volumes are ranging from 100 to 500 meter cube with capacities of 100 to 1000 tons a day. Iron ore is reduced by carbon monoxide generated by coke combustion. We basically have inputs like iron ore or sinter, pellets, then coke, fluxes like limestone, dolomite. These are introduced from the top of the furnace. And from the bottom, we have preheated air, sometimes even oxygen enrichment. And what we get out of the furnace is, of course, output is a hot metal, which is pig iron, some slag, and blast furnace gas. Now, if you look at the main zones in the furnace, you have a drying zone where moisture is removed from 100 to 400 degrees centigrade. We have a preheating zone, which is from 400 to 900 degrees centigrade, where indirect reduction takes place, where Fe2O3 gets converted to FeO. Then we have a reduction zone of 700 to 1100 degrees centigrade, where FeO reacts with carbon monoxide to form iron and carbon dioxide. Then you have a cohesive zone, which is from 1200 to 1500 degrees centigrade, where iron softens and slag is formed. Then you have a combustion zone from 1800 to 2200 degrees centigrade, where coke burns to produce carbon monoxide. If we look at typical consumption figures per ton of hot metal, we require iron ore to the tune of 1.5 to 1.7 tons, coke from 500 to 700 kg, limestone from 100 to 250 kg, and hot blast air from 1200 to 1800 Nm3. And what we produce is a ton of hot metal, 250 to 400 kg of slag, about 1500 to 2500 Nm3 of blast furnace gas. If we look at the typical composition of the blast furnace gas, we have nitrogen about 50 to 58%, carbon monoxide about 20 to 28%, carbon dioxide about 18 to 24%, hydrogen about 2 to 5%, and oxygen is usually less than 1%. The calorific value of this gas is expected to be around 700 to 900 kilocalories per Nm3. The temperature at which the gas comes out ranges from 100 to 50 degrees centigrade, and the dust load is about 10 to 50 grams per Nm3. It's basically dust comprising of iron oxide, coke fines, flux particles, alkalis, and traces of zinc. Now, this hot gas coming out of the furnace is utilized essentially for hot blast stoves, boilers, sinter plants, coke ovens, and captive power plants. And typical pollutants which we have to deal with in a gas cleaning plant is basically the dust, carbon monoxide, sulfur dioxide to an extent, NOx, carbon dioxide, which is about 1.5 to 2 tons per ton of hot metal. Now, if we look at the work zone hazards that this plant creates, you have CO leaks at times, and then there is dust, heat stress, and H2S traces to deal with. What we can see on the screen is a typical gas cleaning plant where the hot gas from the mini blast furnace is first quenched in a saturator to bring down the temperature and then taken to the venturi. So in the venturi, we have a system whereby we can reduce the cross section by throttling. This can be changed. There is a flexibility in the design which allows you to change the cross section, whereby the turbulence in the throat of the venturi can be increased, and this is very important to ensure high efficiencies which are required to deal with extremely fine powders. So there is a cooling and scrubbing liquid, which is water, which you can see in the recirculation line, and then the gas comes into the elbow, middle elbow, and goes to the next venturi. We are using two-stage venturi to get a better result on the efficiencies, and it also helps to reduce and kill some of the pressure which exists in the gas coming from the blast furnace. So the second venturi also has a adjustable throat, and it is possible to operate it in an auto mode based on a feedback from pressure transmitter. The gases which are essentially cleaned of all the fine powder are then taken to the separator, which is a cyclonic separator, from where the gases emerge out through a mist eliminator where the vapors are removed. In the end, we have a septum valve which helps to reach the desired pressure which is suitable for further processing in the hot blast stoves. And so the cleaning gas is delivered for usage downstream. So there is a typical gas cleaning plant. Which is for a food industry application. This is a food flavor manufacturing system, and wherein we have to remove VOC as well as particulates. So there are two separate systems provided. There is one system which deals with particulates as well as vapors, and another system which deals with only fumes containing VOCs. So there are two different types of scrubbing units provided in the two systems. The one with the particulates and the vapors is provided with a pulse jet back filter for separating the powders, and that is followed by a spray tower to take care of the vapor reduction. The scrubbing liquid in this case is water. Volumes. You can read out the specification. Sir, volume and
Sir. Open the duty language.
Yeah, so as you can see, the gas volume for the system is 21,500 meter cube per hour. Temperature is 60 degrees centigrade. We are handling air and organic vapors. Particle size is 5 microns and above. Dust load is 20 grams, which is not a problem for a bag filter. We have to meet outlet emission of less than 20 milligrams for the particulates. Pressure drop for the filter is 150 millimeters maximum. And then these are the specifications for the bag filter, where we are using the bag diameter of 116 millimeters and a bag length of 3.7 meters. We have a total cloth area of 307 meters square, resulting in a air to cloth ratio of 1.19 meter cube per meter square per minute. Yeah, these are the specifications for the fan.
We'll go for this one.
So here the important aspect was to make sure that the VOCs are handled successfully, and the spray tower and the pack spread tower what we have provided are able to meet the expectations of the customer on the outlet emissions of the VOCs, and of course also of the particulates. So we now move to another system, which is a flue gas desulfurization system. Basically, the application is for a recyclable and a recovery kind of an industry where refinery catalyst is being processed to recover valuable materials like cobalt and nickel and so on. So the first part of the process involves roasting of this catalyst so as to so it's an oxidation reaction, and the gases which come out contain a very high quantity of sulfur dioxide. It is of the order of 5,125 ppm for a gas volume of about 59,000 actual meter cube per hour at a temperature of 250 degrees centigrade. The dust load is expected to be around 5 grams per nm cube. So we can see the system here on the screen where the gases from the fluid bed roaster as well as a fluid bed cooler which is adjacent to that roaster, where the product coming from the fluid bed roaster is cooled and the off gases from the fluid bed cooler are also combined with the flue gas coming from the FBR, that is the fluid bed roaster. So we have a multi-clone first to take care of the particulates, and thereafter we have got a waste heat recovery boiler where steam is produced from the hot gases coming from the FBR. The temperature inside the FBR can reach 500 to 550 degrees centigrade, and as a result there is a considerable amount of heat available, which can be heat and energy which can be recovered. Now the gases which are coming out from the waste heat recovery boilers are taken to a quencher for reducing the temperature to 80 degrees centigrade, and then they are passed to a venturi scrubber to remove the fine particulates that come along with the flue gas. The next step is to take the gases through a threaded elbow in a line absorber. So a line absorber basically has a countercurrent flow of the gas and line slurry, which is employed for neutralizing the sulfur dioxide. At the end of the gas absorber at the top, we can see mist eliminators for taking care of the vapor droplets. And below the mist eliminators, we can see the spray banks from where the line slurry is sprayed in the gas absorber. We have got below the spray banks what we call as pipe decks, which are basically used to straighten out the gas which enters the gas absorber and ensure a uniform distribution inside the cross section of the gas absorber. And it also plays the role in enhancing the neutralization of sulfur dioxide. The outlet gas from the gas absorber then enters a knockout drum where any residual vapors are separated, and then taken to a centrifugal fan, which creates the suction in the entire system. Now the outlet of the centrifugal fan is then connected to a polishing packed bed scrubber, where we use caustic as the neutralizing liquid. So with this two-stage scrubbing, we are able to reach the expected level of 50 milligrams of sulfur dioxide, or rather less than 50 milligrams of sulfur dioxide at the outlet of the packed bed scrubber. So packed bed scrubber also has got inbuilt mist eliminator to make sure that the vapors are also eliminated before they are let out to the atmosphere. Now, since we are using hydrated lime in this system, we have also got a post-oxidation step in the recirculation tank below the absorber, wherein we convert calcium sulfide to calcium sulfate. And so the gypsum produced can be used as a byproduct and can be sold to the cement plants. And there is no landfill to worry about. So we use a vacuum bed filter along with a hydrocyclone for separating out gypsum. There is a dosing system for dosing lime slurry in the recirculation tank of the lime absorber, and similarly a dosing system for dosing caustic in the recirculation tank of the packed bed scrubber. Then there is a material handling system for lime, which is essentially a loading system of pneumatic conveying to load the silo with the required quantity of hydrated lime. And then there is a weighing system where we weigh exact quantity of hydrated lime and then take it into a tank for preparation of lime slurry. This lime slurry is then transferred the dosing tank for onward consumption in the lime absorber. So now that we have seen some of the systems which are based on wet scrubbing, we now go to a few dry systems where my colleague Deepak will explain a ferroalloy based system based on backfilter.
Yes. So should we start with the video?
I Hello, good afternoon. As Mr. Farkesar has briefed about what the particular matters are and the sources, various sources in the industry, and how they are to be treated in different modes of separation, be it wet scrubbing or dry separation and so one so more important industry where this emission is one of the bigger source of emission is the steel industries. And in the steel industries there are ferroalloys which are the intermediary products in the steel making process. So first we will just brief on what are the ferroalloys. It is the alloys of iron combined with one or more alloying elements like silicon, manganese or chromium, even nickel and some. So why these alloying elements are added? Of course, in a steel making process, it is to be added in a molten steel, so that the required chemical compositions and mechanical properties can get, and we can get the required grade of steel. So in typical ferroalloy systems or ferroalloy furnaces, The furnace which is the most we use across the industry is submerged arc furnace. So of course it is different from typical electric arc furnace. The basic difference is the electrodes, which is the graphite mostly electrodes. They are submerged within the raw material charge. It's called as a burden. The process of this furnace or steel making alloy steel making is first this raw material is fed into the furnace. Then electrode which are submerged and penetrated in burden. Then electric current passes through this charge which generates a high temperature which allows this metal oxides to reduce and to produce the required ferroalloys. Some of the ferroalloys are silicon, ferromanganese, ferrochromes. And then this molten alloys in the furnace is then tapped from the bottom along with the slag in a different diagonally opposite lead from the furnace. So there are various types of furnaces: open type, semi-closed type, and closed type. And these are the massive source of fugitive emissions where the gas emerging from this is having a first is particulate matter, and the temperature of gas is in the tune of let's say from 200 to 500 or 600, based on which alloy furnace is scattering or which alloying elements it is scattering. Among the various alloying elements, the ferrosilicon is the one where we face the maximum temperature of the flue gases or of gases. Of course, because silica is a stable element, and for that energy required is high, and of course the gas temperature emerging from the furnace is very high as compared to other submerged furnace catering to the silicon, manganese or ferrochrome. So if we typically then this system contains, since I told about the temperature of the flue gas is very high. So to filter and treat for the back filter, we have to then first make sure that the gases are cooled down in air-to-air heat exchanger, so that the off-gas temperature, which is in the tune of 500 degrees, 400 to 500 centigrade, this needs to be bring down to the operating level so that we can select the filtering cloths or filter bag material accordingly. Generally, if we consider a polyester needle felt, then we have to that delta of 500 to 120 degrees centigrade, we have to bring down through this heat exchanger. So off gas coming from the furnaces, it is to be tapped from the emergency stacks, which is at the top of the or tap at the top of furnace. Then, of course, it is having a electrically operated damper or pneumatic operated damper, which is installed in the tapping lines of the furnace and, of course, in the stack. So these gases will then flow through this heat exchanger, where the flue gas is temperature is reduced from 500, 400 degrees to 120 degrees to atmospheric air through this axial flow fan. This will bring down the temperatures while it's a single pass or double pass configuration of heat exchanger. And the outlet of this gas, of course, with the temperature of 120, and then goes to the filter bags. The challenge in treating these gases or off-gases is that particulate matter which are in the particle size are even go to the submicrons. In many cases, it ranges from 5 to 10 milligrams. So, of course, the selection of baghouse keeping the air to work ratio is the vital in this. Because since these are tiny and submicron particles, we have to carefully select the cleaning methods. Of course, it is the offline cleaning method, and with air to cloth ratio and the entries of back filter casing entry to be given, so that we can have get rid of this re-entrapment of the dust since the micron size are very less. So air to cloth ratio generally to be kept below 1, so that there should not be any differential pressure issue across the baghouse. So with careful selection of ACR, air to power ratios, type of entries, and of course the pulsing system where right size of pulse wall also plays a vital role to keep the operate and differential pressure across the backfill so that we can get the required draft and we can make sure that the operational and occupational zones should be free from the local fugitive emissions and the required draft maintained at the top of furnace. So typically these systems also includes the dilution layer damper, where in case any trouble in the heat exchange in the case of issues in axial flow fan and if not we got the data across the heat exchanger, then outlet temperature might shoot beyond the range of selected filter bags material. Then in that case, with the loop of temperature element and the temperature transmitters, with temperature loop, we can open with the regulative duty type damper where proportionate opening of damper makes sure that atmosphere is directly mixed into the hot gas, and this brings out to the temperature well within the limits of operating of selected filter bag medium. So we have a brief video showing the process, the video, which is just playing so that you can have an idea of how this system total works. Yes. This is the brief process of this and typical factory layout or plant layout for this furnaces, which are typically in MVA, they specified as the furnace capacity, 9 MVA, 30 MVA, 16.5 MVA. These are the furnace capacities where they have defined as a longevity limits capacity. This is a typical layout where, as I shown over there, the submerged arc furnace and one tapping duct is there from the submerged arc top release, which first flows to the heat exchanger, air to air heat exchanger, where we also look this axial flow fan with the inlet temperature, and we can optimize the consumption of power to this number of active flow fans running in condition based on the inlet temperature. It will all run conditions when temperature is at peak, and it will off some of the fans based on the inlet temperature. And there is a dilution damper where, as I said, if it is a shoot up of the temperature, then this dilution damper will open in proportionate with the amount of air required to make sure this outlet temperature can be achieved. Followed by baghouse with offline cleaning mechanisms with multi-chamber compartmentalized design. Generally, entry of a baghouse is at the casing, so that we can get the proper can velocities, or more specific, it's an interstitial velocity, so that this re-entrapment issues we cannot surface because of this micron and fine particles, so that we can ensure this delta P across. Main challenge in these fume extractions of furnace dust is the handling of the dust, because these are very fine fluffy materials which is uncontrolled when the proper velocities are not maintained within the chamber. And of course, this side fan which creates the suction, and this is size based on the pressure drop of the equipment, backfilter, heat exchanger, interconnecting ducting, and the required draft at the furnace. So this is where we can adhere to the fugitive emissions coming from submerged. So I'm just asking Mr. Dominic to have some light on the ESP, electrostatic precipitator.
Yeah, maybe you can talk about the practices for healthy operation of the ESP, and similarly something on the troubleshooting aspects.
Hello. Okay, good afternoon, everyone. Okay, when we talk about responsibility in operating electrostatic precipitators, I'm pretty sure that most of the plants they have a few points in mind. And most obviously, something that is starting with internal maintenance, maintenance of the ESP internals like collecting plates and discharge electrodes, wrappers, and other auxiliaries. So I don't have to very specifically say anything about that, except saying that you must ensure that your collecting plate and discharge electrode alignment should be perfect. The electrical clearance should be maintained. I think that those sort of things are mostly known to everybody. But if any specific questions on that front, I can definitely address it. But here I would like to stress more on certain points which are not widely known or widely, taken care of because of this lack of the impact that kind of things have on the performance of the ESPs. So one thing to start with is that, is the leakages, false air leakages into ESPs. False air leakages into ESPs are mainly can lead to mainly two types of issues, or three types of issues, I would say. One is that if the false air leakage is sufficiently high, it simply adds to the gas flow which the ESP treats. That means an ESP that is designed for, say, X meter cube per hour of gas may have to treat 1.5 or 1.15x types of gas flow if the leakage is of that order, 10% or 15%. And it is not very rare. I have seen in many places that these leakages can be as high as that if some important issues are not properly addressed. An example is that I have seen two identical ESPs in a paper plant. Basically, that ESPs are coal-fired ESPs only, but it's in a paper plant. Both are identical, and both are loaded, supposedly loaded identically. But one of the ESPs is working very fine, the other one is not. There is always an emission, and the customer has done a lot of work internally addressing the alignment and things like that. But one key point that they have missed is on the near the inlet expansion joints in an area where it's not very easily visible. There was a huge wearing out of the expansion joint, and through that a lot of air leakages was taking place. This somehow has escaped the attention of the customer, and these kind of leakages have got two impacts. One is that it adds to the gas flow, as I have already said earlier. And the second aspect is, in a power plant where a coal is fired or any other fuel is fired, you get a lot of moisture in the flue gas. Right from even in the worst coal will have result in something like 8 to 9% of moisture in the flue gas, whereas some good quality imported coal and certain things like lignite and other things will have up to 25% of the moisture in the flue gas also. Now, moisture in the flue gas is something that really works in favor of good performance of the ESPs. So the ESP designer would have definitely taken that percentage of the moisture which is likely to have in the flue gas for that particular application while sizing that ESP and designing that ESP. But if you allow false air leakages through the either inlet duct or any other point like what I have seen, what happens is atmospheric air is never that high in moisture as compared to the flue gas. So this addition of flue gas will lower the moisture content of the flue gas in the ESP, and that leads to a higher resistivity of the flue gas and dust which is treated by the ESP. And as you know that ESP electricals is all about how resistive the dust is. And if that happens, then the performance of the ESP is going to go down. So that's one thing that's beyond the limits of the flanges of the ESP, something that happens and affects the performance of the ESP, false air leakages. So one should be very alert to this aspect of the process. Another aspect is any false air leakage which is happening at the level of the hoppers, that is the bottom of the ESP or the conveying mechanisms. Even if that fault share is very minor, even if that's of the order of 1% or 2% of the gas flow. But depending on the location where that leakage is there, it can have a serious impact on the emission by way of the phenomenon what is called the re-entrainment of the dust. This can happen more and extremely at the last hoppers of the ESP, that is outlet side hoppers of the ESP. If you have some leakages through the outlet hoppers, that dust which is kicked up will not go to the treatment zone of the ESP again, it goes straight to the chimney. So even if the rest of the ESP is working perfectly electrically and mechanically and probably giving an emission of 30 milligrams, say, but the dust kicked up from the hopper can easily increase the emission from 30 to 60. That's quite likely, and it can be even more depending on how serious the leakage is. So what the Pollution Control Board or what you ultimately are worried about is the emission that is going through the chimney, not what is coming at the outlet of the ESP per se. So please take care of this aspect very, very carefully, that the leakages through any point of the ESP that can very seriously affect the ultimate emission goals of your plant. And the second aspect is what I would like to see is about the electricals. Very often, general perception is that the more power you pump into any ESP, that is, increase the voltage, increase the current, and you are likely to get a much better performance. That also need not be true in many cases, because if most of the large power plants in India, what you have is a problem of highly resistive coal. The coal that is being used is highly resistive, that when it is fired and passed through the ESP, you encounter the problem of what is known as back corona. And explaining back corona is a little complicated because I don't think that I can do it at this moment through this talk. But only please understand that when back corona sets in, what really happens is, beyond a certain level, if you go on increasing the power to the ESP, the performance actually deteriorates. It's rather than emission coming down, emission will go up after a certain level of threshold. So traditionally, this problem has been addressed by large OEMs like BHEL and all that, through some method called charge ratio charging. That is, the transformer rectifier panels will be operated through a mode called charge ratio mode. And that is only what you can say is a kind of a compromise. Okay, you are just limiting it to that threshold level above which the problem is likely to happen. You will limit the energy to that level. But ESP, because of the large areas, collection area that ESP has, it has got much more potential to perform better than that. So only this back corona is preventing ESP to perform better than that. So the technology of recently this technology has become a little more cutting edge technology. Technology has improved, and thereby there are more better electrical charging methods through which this problem can be addressed. As a general term, that kind of charging is called HP pulsing, high voltage pulsing. That is, normally if you use a transformer rectifier of say something like 80 kV peak or 100 kV peak or 105 kV peak, that is the maximum peak that you expect the transformer to operate at. But the new technology allows you to superimpose another narrow pulses over this peak, so that your peak can be taken to even larger levels. So for example, a 105 kV peak tier set, which typically operates on the load at something like 60 or 70 or 80 kV peak, that can be raised to 100 or 105 or 110 by usage of this special type of transformers called pulse transformers. So such technology can overcome the effect of back corona, and so those are the new technologies available in the world today. Of course, right now those technologies are little complicated and costly, But over a period of time, I'm sure these technologies are being fine-tuned and become more affordable. And any responsible customer who wants to keep his plant absolutely low emission should look forward to this kind of technologies also and see how best it can be utilized in their plants. And another kind of electrical technology that is being used is for low resistive application, low or medium resistive dust applications, and that is called three-phase TR sets, and high frequency TR sets are also being used. Again, these TR sets can improve the performance for the existing ESP and existing mechanical conditions, say up to the level of reducing the emission by up to the level of 50%. So provided you choose the rating and the place where you install it. Place in the sense, what I mean is every kind of TR set is not suitable for every field of the ESP. For example, the inlet field of the ESP will respond to a particular kind of technology better, and the outlet field of the ESP, where the more finer particles are being collected and overall current levels are likely to be high, there a different kind of technology will work better. So even in the same ESP, it's very common nowadays that you use different types of technology with proper study and analysis. So these are the two things that in the new world, when you talk about reducing emission to the level of even 10 milligrams or less, these are the technologies which are coming up. Of course, ESPs have got a limitation in collecting very low micron particles. That has been traditionally the problem with the ESPs. But of late, it's not uncommon for ESPs to have an emission of as low as 10 to 15 milligrams per nm cube emission also, with proper use of electrical technologies. And from operations point of view, another point that I would like to mention is about the conveying equipment below the ESPs. At least in many of the power plants, where you don't find any other reason for a sudden increase in emission. Like I have seen many people found that ESP, which has been working quite well, suddenly has developed a problem in the problem of emission. So in most of such cases, this problem really does not get traced to the ESP itself, but the problem is really with the auxiliary equipment like the conveying equipment. If conveying equipment are not designed properly, or the original design is fine, but if you start using a different type of coal with higher ash content, or you upgrade the capacity of the plant without upgrading the capacity of the conveying mechanism, there are different such possibilities are there. If any such things happen, then you will have a sudden problem of re-entrainments and more emissions, even if every other part of the ESP is working good. So anybody who is in charge of maintenance should also be particularly careful about the auxiliary equipment like the conveying equipment. So that is very important while doing the troubleshooting of any ESPs. Now coming to another important aspect, which is called the wrapping. Most of the customers often feel that the wrapping is not sufficient in an ESP because they find a little bit of coating on the collecting plates and discharge electrodes. But again, here I would say that over 80% of the cases I have found that insufficient wrapping is not the issue of performance, but excessive wrapping is the problem with many ESPs. What can cause this is that excessive wrapping, rather than excessive wrapping might make your plates cleaner, but making your plates cleaner means what? You are actually hammering it with such force and such frequency that all the fine particles which are stuck to the plates are not really falling into the ESP, falling into the hopper, but rather they are also getting re-entrained. So what I mean to say about over wrapping is that you don't have to wrap very frequently and very forcefully every plate, every discharge electrode, because it should allow some coating to happen in the collecting plates and discharge electrodes, and then wrap in a way that the dust is dislodged in a an agglomerated form rather than flying in a powdery shape. So this is another common misnomer which is prevalent in the plants, that if something is really wrong with wrapping, it must be that wrapping is insufficient. No, most of the cases it is better to optimize the wrapping by delaying the wrapping and then controlling the emission. That is found to be a more useful method of adjusting the wrapping to the requirement. And a fourth point I would like to emphasize is on the gas distribution of the ESPs. In earlier days, that is about 20 years back, and all this aspect was not very seriously taken up by many customers because the technology was not up to the mark at that time. Anything to do gas distribution or gas flow correction means taking shutdowns and conducting gas distribution test within the ESP, going into the ESP and then trying to do some correction, which is a very cumbersome process and often does not result in any good result. But with the arrival of CFD technologies and other things, it is much more easier now. If your ESP is okay in every respect, still it doesn't have good performance or expected performance, one hidden problem could be the gas distribution related problems. Now, without taking a shutdown, you can very easily address this problem by conducting a computerized fluid dynamic study, CFD studies. And CFD studies will reveal a lot of things, not only on the distribution of the ESPs, but also the hopper re-entrainment problem, which I mentioned earlier, especially on the last few outlet side fields and all that. And without taking a shutdown, you can parallelly do this CFD studies and verify the real nature of the gas flow inside your ESP and design whatever rectifications that are required. And the rectifications that are required often are very simple. You will require a few baffles here, a few diverter plates here, and often it also will lead to a reduction of the pressure drop in your ESP as well as the ducting. So that is the additional benefit that you are getting, that your fan will have a much more margin, with a lower pressure drop and in ESP as well as ducting. So this aspect also needs to be very seriously considered for ESPs which you feel are not working up to the expected standards, or ESPs which you would like to improve the performance. So I would like to stress on these few points at the moment, and if there is any question, I can take that.
Okay, sir. Thank you, sir. Thank you for the. So now we would wait for anyone. If we have any question, they can drop it in the chat, and we will take it over. So, or they can, yes. So we will wait for 5 minutes, and if there are no questions, then we will wrap up the webinar. Okay, I think there are no questions. So we will wrap up the seminar. I would like to thank Dominic sir, Deepak sir, and Padke sir for joining the webinar and giving us their valuable time and also information about the changing, how the effluent parameters are changing, how the norms are changing, and how we can deal with them in different industries and different applications. So thank you everyone. Thank you for joining.
If they have any question, then
if you have any sort of question, you can also inquire us at RIECO.com, and there are also contacts. If you visit our site, you can see different types of solutions that we offer, different industries that we cater to, and different effluents or different problems in industry that we are solving. So not only in air pollution control, we are also doing it for clean air and also grinding solutions. So feel free to visit us, reach out to us through our website or the call numbers or the WhatsApp numbers, so that we can help you out with the problems that you are facing. So thank you everyone.
मी बघितलं